In this lesson, we're going to be talking about bonding. We're going to take all that stuff we learned in the previous unit about the structure of the atom, in particular the structure of the electron cloud, and use that and build on that to understand how bonding takes place. Both ionic bonding, where electrons are exchanged, and covalent bonding, where electrons are shared. So when we talk about bonding, we're going to relate this to all the stuff we learned about structure in the last unit. We're going to start with ionic bonding. And often when we talk about ionic bonding, the place we start is with binary ionic bonding. And binary ionic bonding just means we have two elements. Binary in chemistry doesn't mean two atoms, it means two elements, okay? So what we think about, the way we like to think about it or talk about it when we're starting out talking about ionic bonding, is when we have two elements that are bonding ionically, that one of those elements, or the particles of that element, the atoms of that element, is going to give up one or more electrons, and the other particle or particles of the second element are going to gain electrons. Okay? That's the way we think about it. Now, that's not always what is actually happening, but it's a way to think about it. It helps you kind of get into the idea of the way things happen. Now, if I have an atom that gives up electrons, it gains a positive charge. Here's the reason why. An atom is neutrally charged. So let's just look, example, at beryllium. Beryllium has 4 protons and also has 4 electrons if it's a beryllium atom. Okay? Protons are positive, electrons are negative, so a beryllium atom has all the positive and negative charges canceling each other out. A beryllium atom is neutrally charged because it has an equal number of protons and electrons. If beryllium gives up electrons, then it has more protons than electrons. Protons are positively charged, electrons are negatively charged. So if I give up electrons, this becomes a positively charged particle. And it's no longer an atom. When it becomes a positively charged particle, it's now an ion, actually a positive ion. And we happen to call positive ions cations. Okay? Now, on the other side of that, if we have something gaining electrons, then it's no longer an atom either. It's a negatively charged ion. All right? Chlorine, for example, has 17 protons and 17 electrons if it's an atom. But if it gains an electron, now it has 17 protons and 18 electrons. Electrons being negative and protons being positive, that means this chlorine with 18 electrons is now negatively charged because it has an extra electron. That makes sense? And that's what we're talking about. That's what we think about it when we talk about ionic bonding. Okay? So ionic bonding can be thought of, I don't know if you can call it a definition, but it can be thought of in this way. It happens when you have oppositely charged particles attracted to each other. Oppositely charged particles attracted to each other. And when I say particles, I don't mean like dust particles, okay? I mean particles much smaller than a dust particle. We're talking about particles the size of atoms or molecules. Oppositely charged particles that are attracted to each other, and these particles are the sizes of atoms or molecules. Okay? There are certain types of ions that are kind of like molecules, only they have charges, just like those monoatomic ions have. Since I used that term, let me explain. Monoatomic means one atom. Okay? That makes sense, right? Monoatomic? Okay. So what I want to do is to start with the concepts we were using in the last unit with orbital notation. Let me have you go ahead and write out the orbital notation for sodium and the orbital notation for chlorine. Write out the orbital notation for sodium and write out the orbital notation for chlorine. A word of caution, I want you to do it in pencil because you may be changing some things, okay? Write out the sodium and chlorine orbital notations. Okay, so this is the orbital notation that I have for sodium. I purposefully drew that last electron in red. I'll show you why in a minute. To remember how we did that, let's go back to our SPD and F sublevel region periodic table outline. If we look at the periodic table, sodium is located right here. So it is in the s sublevel region. That doesn't mean it only has s orbital electrons. It means that that the highest energy level, the valence level, will have s electrons. So what we're going to have is, now helium actually belongs over here when we're talking about s, p, d, and f. And so the placement of hydrogen and helium tells us I have 2 electrons in an s orbital. And then I go to lithium. 2 electrons for lithium and beryllium, or by virtue of their position, tells us we have 2 electrons in an s orbital here, and then 6 electrons over here for boron through neon in that second primary level and the p sublevel. And so here's our 2p and 6 electrons with 2 electrons in orbitals. So I have a total of 3 orbitals. And finally we get to sodium, again in the p sublevel region. So I've got that 1 electron in the p sublevel region. Okay. Chlorine just continues out that row. So here's sodium. We're going to have 2 electrons by virtue of the position of sodium and magnesium. So 2 electrons in 3s. And now we're in the 3rd row, corresponding to this 3rd primary energy level, represented here by this coefficient 3. And this is the p sublevel region, as we can see here, p sublevel region. And so we've got 1, 2, 3, 4, 5, 1, 2, 3, 4, 5 atoms here, or elements as we go across, and that tells us we're going to have 5 electrons. Okay, 1 electron in each orbital, coming back and pairing up 2 more. That's how we get the orbital notations. Now, for the bonding that takes place between sodium and chlorine, and as long as we're talking about monoatomic ions or single atoms or binary compounds like this, where binary means just 2 elements, you actually do have an exchange of electrons. That doesn't always happen, but if I could get pure sodium metal and pure chlorine gas, we're going to get an exchange of electrons when they combine. It actually does happen that way. But so what's going to happen here is that for sodium and chlorine to bond, sodium is actually going to give up its 1 electron. Now we're going to relate that back to some more of our periodic table outlines. Okay, here's first ionization energy. Remember that everything over on this side of the periodic table has a high first ionization energy, and over here has a low first ionization energy. So sodium is located right here on the low side. It gives up an electron easily, much more easily than, say, chlorine does over here. Okay, the flip side of that is electron affinity, and chlorine's over here. It wants to really hold on to new electrons. It wants to get new electrons. It gives away a lot of energy when it gains an extra electron. Okay, so chlorine wants to gain an electron. Now, in terms of orbital notation, then chlorine will get that 1 electron in the missing slot in its remaining half-full orbital. Okay, does that make sense? Okay, now sodium is going to lose this electron, and when you do that, you end up with losing that entire energy level, and now we've got a full valence level there. Or it's not really the valence level, but what remains is a full outer energy level. Does that make sense? So what we end up with when we're done, as you'll see, is we'll have 8 electrons in the outer level of chlorine and 8 electrons in what remains as the outer level of sodium, which fits our octet rule. Okay, atoms tend to want to have 8 electrons in their outermost energy level. Octet meaning 8, right? Okay, so that's what's going to happen. We're going to take this electron right here, and we're going to completely remove it, and we're going to put it down here. Okay, and so let's put that electron in here. Okay, and let's take it out of sodium. So I'm just erasing the electron in that 3s sublevel, an orbital, when in fact what we've done by eliminating that 1 electron is eliminate that entire that whole energy level is gone now. Okay, technically it's not there anymore because that electron's gone. Got it? Because you only have 1 electron there. Now, the result then is that a sodium atom had 11 protons, and therefore an atom is going to have 11 electrons. Since we got rid of an electron, we now have 11 protons, positively charged, and 10 electrons, negatively charged. So overall, this sodium is not an atom anymore. It's an ion with a positive charge. I can't leave that like that symbol like that, when I've gotten rid of this electron. I need to show that it's a positive charge, and so I'm going to put a positive charge symbol in the superscript position here. Okay, upper right. All right, now chlorine, on the other hand, it gained an electron. It had, when it was an atom, 17 protons and 17 electrons. Now it's got 17 protons, and 18 electrons. So it's got one more electron than protons. It is now negatively charged. Okay, so just like with sodium, I'm going to put a charge symbol on here. It's going to be a negative charge. Now, the one thing you need to know about this, well, I don't have to say it right now, but I'm going to. When you have negatively charged monoatomic ions, okay, negatively charged monoatomic ions, meaning monoatomic meaning one atom, okay, so an ion made from one atom, negatively charged because it's got an extra electron, negatively charged monoatomic ions, we now change the name of this. It's no longer chlorine, it's now chloride. Okay? So negatively charged monoatomic ions. When I say negatively charged, I don't mean just one negative. It can be two negative or three negative. Negatively charged monoatomic ions have the name of the atom changed so that it has an IDE ending. Okay? You follow me? All right, so that's now chloride. We don't change the name of sodium. We just call it a sodium ion. Okay? I don't know why. We do it with, well, I know why, but it doesn't matter right now. Okay? We just change the end of the name to ide. Okay? Got it? So it's now chloride.
That's only if they have a negative charge?
Only for negative charges. That's right. Only for negative charges. Okay? All right, so let me sort of throw you guys in the lines then a little bit. Let's do this. Let's do this with electron dots. Remember electron dot formulas, right? How many electron dots should a sodium atom have? Just one, because it had originally one electron in its outermost energy level, highest energy level, right? So here's the symbol for sodium, and here's one electron dot. Now I put it on the right, but you could just as well have put it on the top or left or bottom. Okay, doesn't really matter. How many electrons did a chlorine atom have in its valence level? 7. So how many dots do I put around a chlorine symbol for an electron dot formula? 7. Okay, so let's do that. One on each of the four sides, and come back and pair up on any of the other three sides you want to get 7. I'm going to put them here, here, and here. Okay, nothing special about where I put them. Okay, so in order to show this same idea for electrons being moved from here to here, I can just draw an arrow here to show that I'm moving that electron. But to make it make sense, I've actually got to have a second picture here to show the result of that. Okay, so I'm drawing an arrow to show that's where it's going to. So now we're going to have sodium here with no electron dots, and chlorine with 8 electron dots because I put an extra electron on there. Okay? Sodium is going to have that positive charge because it got rid of an electron. Now chlorine will have a negative charge. Okay, I'm going to put it over here and kind of out of the way a little bit, because when I do it for chlorine, if I just put that negative up there, it's not clear that that negative only applies to an extra electron or if it applies to the whole thing. And since it applies to the whole thing, I really need a way of showing it applies to the entire thing, and I'll do that by putting a bracket around it with the negative sign outside so that you can see that negative charge applies to the whole chloride ion. You follow me? Okay, so we're doing it with orbital notation, we're doing it with electron dots. Now I could do it with electron configurations. It doesn't really make as much sense, but let me show it to you. We won't be using it past today, but I'll just show it to you real quick. Here is sodium's electron configuration. So 1s2, 2s2, 2p6, and 3s1 is what we're starting with. Whoop, 3s1. And chlorine is 1s2, 2s2, 2p6, 3s2, 3p5. So I could do it like this and say this electron is going to go down here, and then show the result of that, and say that sodium, this sodium is now 1s2, 2s2, 2p6 with a positive charge on the sodium because we've removed an electron. And the chlorine, 1s2, 2s2, 2p6, 3s2, and 3p6. And since it gained that electron right there, this chlorine is a chlorine ion or a chloride, and it has a negative charge. One of the reasons for me showing you this is to make this point. Sodium without that electron, sodium without that extra electron, has the same electron configuration as a noble gas. Here's the configuration for neon. Okay, notice it has the same electron configuration. And chlorine, with that extra electron, has the same configuration as argon. Okay, so both of these have managed to get an electron configuration that matches that of a noble gas. Again, we got the octet rule. Okay, 8 electrons in the outermost energy level. Got all that? All right, so all this is kind of like dovetailing together to help us understand all these things. Okay, all right, so let's do now. I'm going to assign for you guys to try one for yourself. Okay, and you may struggle a little bit. That's okay. Struggling is not a bad thing. Let's do the orbital notation. Let's see, how do I want to word this? So using orbital notation, and electron dot formulas, determine the correct combination of calcium and bromine showing all your work. I mean, you should always show all your work, but I'm specifying it clearly here, okay? All right, so we're going to use orbital notation and then electron dot formulas to determine the correct combination of calcium and bromine showing all the work, okay? So the calcium orbital notation looks like this. We have 2 electrons in the highest energy level, that's the 4th energy level, and the S sublevel, we stop right there, okay? And then bromine looks like this. So we had a 3D sublevel this time because when we get into this transition elements area here, the periodic table, it's dropping back from 4, the 4th primary level, to 3, the 3rd primary level for that D sublevel region, okay? So there, and then we have those remaining electrons over here, 5 electrons in 4p, 1, 2, 3, 4, 5 to get to bromine, and so I have a total of 2 and 5 or 7 electrons in the 4th primary level, the highest energy level. Okay, so to fill this one up, it needs 1 more electron. Okay, but calcium, remember, it's one of those elements that easily gives up electrons because it has a low first ionization energy. Okay, bromine over here wants to gain electrons, has a high electron affinity, wants extra electrons. So bromine is going to want to gain an electron. Calcium is going to want to get rid of both of its valence electrons. So one of those valence electrons can go from here to here, and that gives bromine one extra electron and fills up its primary energy level, giving it a negative charge, but that calcium still has an electron to get rid of. Okay, so we need another bromine this time. Alright, so now I can take this other valence level electron in calcium and put it down here. So now this bromine is a negative charge. I'm going to get rid of, in my orbital notation, the electrons in the highest energy level up here. And now, because calcium has lost 2 electrons and therefore has 2 more protons than electrons, it has a 2 positive charge. Okay, does that make sense? All right, I see some of you kind of writing some things down. I take it you didn't quite get that answer. That's okay. All right, part of this process is designed to be this way. For some of you, it's figuring it out on your own. You'll figure it out correctly. For some of you, you have some misconceptions, and it helps me to be able to dig out your misconceptions and replace it with proper conceptions. Okay? If I just showed you the right answer, it might not be effective. It depends on the student a lot of times. But what I'm doing is piling on a new conception to a misconception, and that's like having a bad foundation on a house. Okay? What we want to do is try and pull out the bad stuff and replace it with good stuff. That makes sense? So let's find a way to sort of identify where your misconceptions are. Then we're propagating your own errors, and we don't want to do that. I want to try to find a way to identify, or help you identify, really, when you have a misconception about the way things work, and replace that with the stuff you want to replace it with. Okay? So don't feel bad if you didn't quite get it right. Okay? If you struggle with it. Valence electrons. Using electron dots like this, it's easy to see that bromine has 7 valence electrons. That's all we put around the symbol when we're doing electron dots, is just the number of valence electrons. That's where we start anyway. And calcium has 2 valence electrons, so we can take 1 electron and put it down here, and that takes care of bromine. Bromine's now going to have 8 electron dots when I finish everything up, but calcium still needs to get rid of 1. So I can't stick an extra one on bromine, because bromine can only take 8. Okay? So I need another bromine for that extra electron to have some place to go. And now calcium has gotten rid of both those electrons. Okay? It has low first ionization energy, so it's easy for it to get rid of those electrons. And I drew a bromine down here. I was going to put it down here. Bromine over here, it has a high electron affinity. It wants to gain electrons, and so I can put that electron right there. And so what we're going to have to do is redraw these now, like you're drawing in a comic book or something. Okay, where you have 2 different panels. Y'all know how to read comic books, right? I'm not telling you. Okay, good. Just want to make sure. So I'm going to draw an arrow to show that's what we're going to here. But it's kind of like in a comic book. We go from one panel to the next. So now calcium has lost both of its electrons. We're not going to draw any electrons on there, but it has 2 extra protons now because it got rid of those 2 electrons. That means it has a 2+ charge. And now I've got 2 bromines. Each bromine now has not just the 7 electrons it started with, but an extra one. Okay? I'll make this last one, this extra one, red just so you can see it clearly. And in order to show that this negative charge applies to the whole thing, I really need to put brackets around it. Okay? That makes sense? Now I can draw 2 of these bromines in brackets, or I could just put a coefficient 2 in front of it to show I got 2 bromines. Make sense? Everybody good? All right then. Should we practice another one? Are you good?
Another one.
Another one? Okay. Another one. All right. I hear more or less a consensus to practice another one. Okay. So let's do orbital notation, electron configurations. Not electron configurations, I'm sorry, electron dot formula is what we want. So used to the last unit when we're doing electron configurations right after all orbital notations, we want electron dot formulas here. I'll come back and flesh that out in a second. To determine the correct combination of, let's say, aluminum and oxygen. Okay. Most of the world, by the way, doesn't spell aluminum that way. Most of the rest of the world spells it with an IUM instead of a UM, and they pronounce it aluminium. So if you ever hear somebody say aluminium, you know what they're talking about. You're right. And when we get it all done, this is what we end up with. So now both these aluminums are going to have a 3+ charge. All the oxygens are going to have a 2 negative charge. And add up all the charges. When you add up all the charges, what do you get? A 0, which is the point. We want to end up at the end, because we no longer have neutrally charged atoms. Now we're going to have a neutrally charged compound. That makes sense? All right. So it increases the stability of the overall system. Now, if I have aluminum using electron dots down here, then I can take 2 electron dots and move them over here to oxygen. That gives the oxygen all the electrons it wants. It wants 2 on each of the 4 sides to get 8. But aluminum needs to get rid of another electron dot. So for that, I'm going to need another oxygen. And so I can put 1 electron dot here, but then this oxygen is going to need another one. So I need another aluminum. So that I can move another dot here. Now that oxygen has the 8 it wants, but this aluminum needs to get rid of 2. So I'll build another oxygen over here and move the remaining electrons over here, and everything's all taken care of. Okay. The result then is that we have aluminum with no electron dots and a 3+ charge, because for each of those aluminums I got rid of 3 electrons, and the oxygens have 2 extra electrons, so they have now a 2 negative charge. I've got 2 aluminum, so I could write aluminum like this twice, or I could put a coefficient 2 here. I could write this symbol here 3 times, or I could just put a 3 here. Okay. Now I want to go back just a little bit to those other formulas we wrote. Let me find that where I did that. Okay, here's one for calcium. Where's one did for sodium chloride? What did I do with that? Okay, so we have, when we do this, end up with this process here, we've got 1 sodium and 1 chlorine, and 1 sodium, 1 chlorine. Okay, so the formula, the ionic formula, also called the formula unit for a combination of sodium and chlorine, then is just NaCl. We have 1 of each. Okay, the ionic formula or formula unit for a combination of sodium and chlorine is NaCl. The ionic formula also called the formula unit for a combination of calcium and bromine, calcium Br2. So I use coefficients to show there are two of the individual particles, but when I show them combined, it becomes a subscript after the symbol. That makes sense? All right. And so then for aluminum and oxygen, the formula unit is, what is it going to be? Al2O3. Very good. Okay. Notice the metals are always written first. Okay. The more positive part of the formula is always written first. Okay. Generally speaking, that means that if it's two elements, if it's just a binary compound, what is further to the left on the periodic table is written before what's further to the right. Okay, because metals are on the left and nonmetals on the right, one way to think about it. Okay, so that's your introduction then to ionic bonding. I want to introduce you to covalent bonding now. Okay, so covalent bonding is the sharing of electrons. Now, almost all the time, when we bond a metal, and metals are over here, there's that stair-step dividing metals and nonmetals over here. Metals over here, we combine metals with the nonmetals that are up here, okay, in the upper right, we get ionic bonding. Okay, metals give up the electrons, nonmetals gain the electrons. When we combine two nonmetals, they're not going to give up and gain electrons. There's not enough difference in their ionization energy and electron affinity to cause that to happen. What we're going to do is share electrons when we're combining two nonmetals. That doesn't always happen that way, but almost always it's going to happen that way. So the classic example, of course, I think is water. So if we have H2O and hydrogen has one valence electron, which in orbital notation we represent in this way, and we have two of them, and oxygen has this orbital notation, and we did this already when we were doing the ionic formulas for aluminum and oxygen. But instead of one of these giving up an electron and the other one gaining one, they actually are going to share electrons. Okay, so we're going to share this electron with this one and this electron here. The problem is that when you share them, you're not only sharing electrons. Okay, we can't just move the electron out of here and put it down there, or move it out of here and put it up there. They're sharing, and they're not just sharing the electrons, they're actually sharing the orbitals. When you share electrons, you also share orbitals. When you share electrons, you also share orbitals. And those shared orbitals are called covalent bonds. When you share electrons, you also share orbitals, and those shared orbitals are called covalent bonds. Okay? Now, you could think about it as just sort of overlapping these two images. That's what we could think about it like that. Now, it's not correct, but I'll show you how you can brainstorm and think about it here, okay? So I could take the oxygen here and do 1s and 2s and then 2p. So I'm kind of like showing them combining. Does that make sense? It's kind of weird, but that's what I'm trying to illustrate. It becomes a little more difficult to illustrate it. Okay? But that shows them sharing orbitals and sharing electrons. Okay? Now it gets a lot more complex. So our ability to be able to use orbital notation for showing how we share electrons starts to break down. Okay? It gets pretty tough. In fact, this is not even the way it actually happens. Let me show you what happens with carbon and hydrogen. So here's the orbital notation for carbon. And carbon wants to have a full valence level. Okay? How many more electrons does carbon need to have a full valence level? 4 more electrons. Okay? How many electrons can hydrogen share in this arrangement? Only 2. I mean, I can put an extra electron in there, but that's not the same thing as sharing, is it? But I need 4. So this isn't working for us, okay? In fact, we know this is not what happens, okay? What happens is when I'm doing this sharing of electrons like this or this, something happens to these orbitals before or during the process of bonding, and it's called hybridization. Now, what is a hybrid? What? A mixture. So if I have a hybrid car, it means we got a mixture of a gasoline-powered and electricity-powered car, right? If I have hybrid corn, not too many people apparently live on farms around here because I see glassy eyes, okay? Hybrid corn means you have some of the genetic material from one type of corn and another type of corn to get some properties of both, okay? A hybrid donkey and horse, what does that make? A mule, okay? So that makes more sense. You know what that is, all right? So we're kind of mixing some things together to get hybridization. What we're going to be hybridizing are the orbitals themselves, okay? In order to be able to bond 4 times with this, these orbitals got to change, okay? I just completely blasted the English language there. My grammar's terrible. We're going to hybridize those orbitals, okay? So what's going to happen is we're going to go from this to this. And I'm going to take these, I'm going to take these orbitals here, and I'm going to make it into a new kind of set of orbitals, okay? I'm going to combine them together and make a new combined set of these S and P orbitals, okay? Not 1 orbital of S and 3 orbitals of P, but 4 orbitals, all the same stuff, okay? And we're going to call it sp3. Now the reason we call it sp3 is because we have 1 S and 3 P's. That makes sense? Instead of 1 S and 1 P, we're now going to call it sp3 because we're combining them together. We've hybridized them. sp3. Now this particular sp3 set of hybrid orbitals happens to be in the 2nd primary energy level, so we can use that coefficient too. By doing this, I can distribute all 4 of those electrons in 4 orbitals. And now I got a way to bond sharing electrons between 4 hydrogens and 1 carbon to make something called methane. Okay? Allows us to make CH4, which is methane. Okay? That makes sense? I could do it like I did the water up here and just draw in my hydrogens up here and overlap them in that way. Okay? But it kind of breaks down on us a bit. Okay? It becomes hard to show it when we use orbital notation. Now, if I use electron dots, it becomes pretty easy. 4 electron dots around the carbon. Hydrogens have 1. And since I'm going to share electrons, I'm just going to show it sharing like this. Okay? So what I started with were the electron dot formulas that we learned about in the last unit. We count up the number of valence electrons and just put that many dots around the element symbol, right? 1 on each of the 4 sides, pair up if necessary. Remember all that? Okay. Now this actually, we don't leave it like this. We went from electron dot formulas in black. When I included the red circles here, it becomes a sharing arrangement. Okay, so we went from the electron dot formulas to a sharing arrangement. And from the sharing arrangement then, we're going to be able to write something called a Lewis dot formula, where we take the electrons and just squeeze them between the element symbols. So these two electrons right here between this hydrogen and carbon get squeezed in between, they squish side to side, they become that. And these two electrons between this carbon and this hydrogen, they get squeezed together and they squish side to side, so they become that, and so forth all the way around. And now we have a Lewis dot formula, Lewis, L-E-W-E-S, dot formula for methane, whose molecular formula is CH4. Okay? Just counting the number of atoms. That makes sense? Now, that all seems nice and great and everything, but we kind of need to know about what's happening with those orbitals, okay? Remember those balloons we made? We figured out what the p orbitals all look like, and we imagined what the s orbital looked like around it? Okay? Well, we're going to take that and we're going to show how these hybridized orbitals are going to be different, okay? So let's do a few drawings for this. Let's start with a drawing that we did for the unhybridized p orbitals and s orbital, okay? So let's say that this is our nucleus for our carbon, and we need a spherical shape for the s orbital. So let's see if I can come up with something close resembling a sphere here. All right, there's our sphere. Not great, but it's okay. All right, that's our s orbital. And then we had a p orbital, one that comes swinging out toward you and part way behind. I'm drawing it first so I can do all the others behind it. And then we got a p orbital, and there's going to be a second part of this back here in a minute. Got a p orbital where I got an antinode going up and an antinode going down. Okay, I got a p orbital where I've got an antinode going to the left and to the right. Those are the two parts of the p orbital. And now I can finish out the first p orbital I started with, because it's going to be back behind here. All right, remember that? Those are all our p orbitals, right? P, X, Y, and Z. Got that? When we hybridize these, in order to do that kind of bonding we talked about a moment ago, not only do we change the way that they are arranged in our orbital notation, they're actually changing their shape. Okay? Now, in reality, we don't, in our class here, we don't draw it very often this way, but this carbon has these orbitals have different energies. Okay, this energy, this sublevel of p orbitals is less stable and more energetic than this is. This is more stable, less stable and more energetic than this is. So we could write it. We had carbon, and we could put the 1s right here, and the 2s here, and the 2p's up here. And so what we have is we got energy increasing going vertically. Okay, you see what I'm doing? So when we put them together, then the resulting sp3 orbitals have an energy that's in between this S and P. So that energy level, their stability, is somewhere in between. Does that make sense? Okay, so what we need is a set of orbitals, actual three-dimensional shapes of orbitals, whose energy is somewhere between the energy for the S level and the P level. You following me what we're trying to do? Now, that doesn't tell us what the shape is, but that's why we're going to make this shape. It's part of the reason we get there. All right. So let's see what that looks like here. So instead of this shape here, well, I can't get my paper to lift up here for some reason. Okay. All right, so here's our nucleus, and we're going to have not a double node, but a single node, or antinode really, or it looks like that. There's actually an antinode or a node that sort of sticks out behind here, but it's so small and we don't do anything, we just kind of ignore it, okay? So instead of a double node for a P, our sp3 is a single antinode, okay? And then we're going to have another antinode coming out here like this. Okay. Now, the s orbital is going to change into the same shape because it's going to be the same. All right. All these hybrids are the same. Okay. We mush these two different things together to make the same thing. So this hybrid orbital is going to come out toward you. Okay. All right, and then we got one that's going to be back behind this. All right. So, see if I can show you what I want to show you here. That's what we started with. That's what we're ending with. See what's happening? It went from these unhybridized orbitals to these hybridized orbitals. 4 orbitals, 4 orbitals. You see what's happening? So this one is straight up like this. Well, let's see, I'll use the orange one. That one goes up like that. This green one comes down slightly more than 90 degrees. That's 109.5 degrees right there, if you put a needle right through the center of it. And this blue one is 109.5 degrees from both of these. It's coming out toward you a little bit. And then the pink one is 109.5 degrees, but it's kind of going back behind things, back there a little bit. Okay? And that shape is called a tetrahedral. All these angles are 109.5 degrees apart. It's as if you put a needle through the middle of the balloon, here, 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 and back there. All those needles will be 109.5 degrees apart, 3-dimensionally. Okay? Follow that? All right, now, let's see what happens then when we bond. Okay? All right, so here's the nucleus again. And I'm going to draw out these orbitals again. So here's that orbital. Here's this orbital. Here's this one coming out toward you. And then the one that's going back behind here. And then I want to put a hydrogen over here because what we did a moment ago, this is the nucleus of our carbon here. Here's a nucleus for our hydrogen. And it only has an s orbital, right? That makes sense? So these two orbitals then, when we combine or share those electrons, we're actually combining these two orbitals. Does that make sense? And we could have another hydrogen down here, or actually out in front, that is sharing, and one back and behind here that is sharing, and one up here at the top that is sharing overlapping orbitals. Okay? Oh, I'm kind of off the screen a bit, aren't I? See what's going on? Let's see what the shape of the orbitals are going to be. I mean, the bonds are going to be. When we overlap and share these orbitals, this shape changes. Okay, we go from this sort of teardrop shape and this spherical shape to a combined shape we call a bond. Okay? Huh?
You call it what?
A bond. It's a bond. All right. All right, so here's our nucleus for our carbon, and I'm going to move my nucleus for the hydrogens a little bit closer here on both of these. what we're going to, all of these actually, what we're going to get is something that looks like this. There's the shape for those combined orbitals when they become a bond. Okay, and here's a nucleus up here for another hydrogen. And so here's a shape for that bond. Okay. The bond that's coming out toward us, I want to show that in perspective. Those of you who've taken art, you kind of have an idea of what I'm talking about. Okay. And the one going back here, all right. So now we got a molecule that is more or less tetrahedral. That makes sense to you? Let's review. All right, we went from unhybridized orbitals, hybridized orbitals, showing how they're going to bond, and finally what happens when they did bond. How's that? That makes sense? Okay. What? You're still drawing? Okay, that's fine. Forward with that. If this were water, okay? If it were water, then this would be our oxygen molecule, okay? Or oxygen atom, I'm sorry. And then it would hybridize in the same way. We'd hybridize 4 orbitals. But 2 of these orbitals, hybridized orbitals, have 2 electrons, okay? With carbon, all 4 of these hybridized orbitals had just 1 electron, okay? When we did water earlier, we showed electron dots for water, and we showed that the oxygen had 2 electron dots. Okay, where did I do that? There. Well, let's see. Did I do water? I didn't do electron dots for water, did I? Okay, so oxygen has 1, 2, 3, 4, 5, 6. Hydrogen has 1, like that. And so we're going to share these 2, and we get a Lewis dot formula that looks like this. Okay? That makes sense? So 2 of the hybridized orbitals have 2 electrons in them. Okay? So with the hybridized oxygen, it hybridizes in the same way, but 2 of the orbitals have have 2 electrons, and 2 of the orbitals have 1. So with water, then you're only sharing 2 corners. That makes sense? Like this might be sharing here with hydrogen. This is sharing with hydrogen, but there wouldn't be any sharing down here at all. That makes sense? So these 2 orbitals are going to stay exactly the same. Whenever you finally get a molecule, we won't have a bond over here. We'll just have those unhybridized orbitals sitting over there because there's nothing attached to them. You follow what I'm saying? Okay? So one of your homeworks is going to have something like that. Not exactly, but we got a little bit of time left. Let's see if we can go from this shape to what I'm talking about and show you that. Okay? This is for water. Okay? So now instead of talking about carbon being the center here, we're talking about oxygen being the center. Okay? So here's that hybridized orbital here. And here's a hybridized orbital here. Here's a hybridized orbital coming out toward you. And a hybridized orbital that's kind of back behind everything like this. Okay? But we are going to share, we're going to say that these 2 orbitals here have 2 electrons in them. Okay? You want to use dots or arrows? Arrows? So we got both electrons in this one and both electrons in this one. Okay? But now these 2 orbitals have 1 electron because oxygen had 6 valence electrons, right? So 2 of the hybridized orbitals just have 1 electron. Now, if we're going to combine with a hydrogen up here and down here, then these are going to overlap and combine. And these are going to overlap and combine. Alright, so here's our nucleus for our oxygen. We've got 2 orbitals that are not going to do anything because they're already full with their electrons. But the orbital that was here and here, they're going to overlap and share with the hydrogen. And so we're going to get that wiener sort of shape there. That makes sense? Sure, I'll go back to all of them. We're going to review them anyway, okay? We're good. Alright, so let's go through this again. So we're starting with unhybridized orbitals for the oxygen this time. Okay? This particular oxygen in this configuration hybridizes into 4 orbitals. Okay? Then we're only going to share electrons for 2 orbitals because these 2 orbitals already have the 2 electrons. If you do the electron dot formula, you got 2 pairs on 2 sides and 1 electron each on the other 2 sides, right? And so these are our 2 pairs here that are completely full. And this one that has just 1 electron is going to share with 1 electron from a hydrogen. This orbital with 1 electron is going to share with this hydrogen 1 electron. And so what we get is that. You following? Okay. So what you're going to do for homework then, for the corresponding problem associated with this, is to figure out another molecule that's a little bit different from either one of these 2, but based on what I told you. Got that?